Hello. I'm going to go through or walk through the exercise 2, 3, and 4 of the group exercises uh, on the long day of this week. So, and I start with exercise 2, and it's about Stokes and the right-hand rule. And we're given a triangular surface with these 3 vertices, and we're given a vector field. So let's concentrate on the triangular surface. And we should determine a parametric representation for this triangular surface. So let's start doing that. So we have this triangular surface. And it is exercise 2 that I'm doing. And it's given by these vertices 0, 0, 1. And B is 1, 0, 0. And C is 0, 1, 0. Let me just draw this surface. Here we have the z-axis. Here we have the x-axis, and here the y-axis. So, and if you have the 1 mark in each of these axes, then this is point A, this is point B, and this is the point C. So it is this triangular surface that we're looking at. Let's see if I can mark this. So this is surface. When I'm going to make this parametric representation, I think I will need this line here. I call this line y, 1 minus x, and or this is the equation for this line in the xy plane, and then I'll take a point on this, call it P. And if I use x as a parameter, I write here, use x as a parameter, then I can, then P is equal to x, and when x is u, then y is 1 minus u, and z is 0. So the line is in the xy plane. So we have u is in this interval. Now, in order to get the triangle, we will use the line from A to P. So I'm using this line here, and I want to say the vector AP is equal to the initial point, which is O, which is A1, plus a new parameter times the vector AP, and this is the final coordinate, and this is the P coordinate, so this is U, and then it's 1 minus U, 0, and then minus the initial coordinate. So this is O, O, 1. And this is equal, so let's take it here. This is equal to V times U, V times 1 minus U, and then 1 minus V. And you see here, U is still in the interval from 0 to 1, and so is V in this interval from 0 to 1. So now we have a parametric representation of our field. And what we need then is that we need to find out with this parametric representation, we need to find out what is the direction of the normal to the surface. So let's compute the normal. The normal is the derivative of the parametric representation. I should write here that this is the parametric representation of the two parameters U and V. So I differentiate with respect to U, I differentiate with respect to V, and this is, when I differentiate this with respect to U, I get V, I get minus V for the second format, and then I get 0. And then I should cross this with the derivative with respect to V. I get U, I get 1 minus U, and then I get minus 1. So when I calculate this, I get, well, you should use the normal formula for that. Let me say, for the first coordinate, it will be this times this minus this times this, and this will be V, and also for the second and third coordinate we get V. And since V is apart from the point where V is 0, then this is a normal vector that points in the positive direction of the X, Y, and Z plane. Let me draw this on the figure. So if you imagine, I could draw it the red color. So if this is, then this is the normal vector, and it's constant throughout the triangular area. Okay, and if you look at it, then this will correspond to a positive orientation of the boundary. I could write that the orientation A, B, C, A fulfills the right hand rule. Now, in order to continue, we need to calculate, or we have a vector field. I write the vector field here. The vector field is set x, y. In order to use Stokes, we need to calculate the curl of the vector field. So I write here curl of V, that is dx. I use the short form notation, dx, dy, dz, cross z, x, y, so V. And I could write here, this is the nabla operator cross the vector field. And when I compute this, I get the constant vector 1, 1, 1. Now I have all the ingredients in order to compute the circulation. I could write here, I want the circulation around the perimeter of my triangular area. And this will be the dot product of my vector field with the unit vector along the boundary, and then the differential d mu. And using Stokes, this is equal to 0, 1, 0 to 1 of this curl of the vector field dotted with a normal vector. I should integrate with respect to u and v. So this will be equal to the interval from 0 to 1, 0 to 1, and then it will be this constant curl vector, and then it will be the normal vector u dv, and this will be equal to, say, the integral from 0 to 1 and from 0 to 1 of 3b. This is a dot product of these two vectors, du dv. Now, the integrand doesn't depend on u, so this will be the integral from 3v times 1. So this will be 3/2 v squared from 0 to 1, and that will be 3/2. So this is this circulation in exercise 2.